I am tasked with solving the following problem. Finding 5 positive integers a, b, c, d, and e, such that a to the 5th plus b to the 5th plus c to the 5th plus d to the 5th is equal to e to the 5th. Note that there is no limit on how large the numbers can get, so in principle we might not find an answer, but let's try anyway. Here's what I have as a first stab. I have a run function that takes an integer n as a parameter and loops through all combinations of 5 numbers between 1 and n using the itertools product function, and determines if the equation is true. If so, we return it. I'm using itertools product instead of itertools combinations since some of the a, b, c, d numbers could in principle be the same. In the calling code, we tried the run function for some value of n. If it does not work, we add 1 to n and try again. If some solution out there exists, and there does, this code will eventually find it. The problem is this code is really slow, like take a sabbatical slow. I timed it on my machine, and after 46 hours my computer yeeted out of frustration. Let's fix this code. Here are the code changes I made. Note that in the equation a to the 5th plus b to the 5th plus c to the 5th plus d to the 5th is equal to e to the 5th, e must be the biggest number, and the ordering of a, b, c, d does not matter since addition is commutative. In other words, we can add integers in any order. This code is much faster since we don't do the expensive if check by comparing the numbers first. Itertools combinations would have done this for us, but we need to allow some numbers to be the same. This version is still really slow and finished in roughly 17 hours. On to the next version, which avoids the if check altogether by making nested loops, where each of the inner loops starts at the previous one's current value. A small speedup is that the e number has to be strictly larger than d, since it's on the right-hand side of the equation. The elimination of the if check gave approximately a 2x speedup running in about 9 hours. Let's make this slightly faster. Note that if a, b, c, and d were all the same, then e cannot be too big of a number. It turns out that if you stare at the problem long enough, e cannot be more than twice the value of d. But we don't want to search further than n, since that's the limit. Otherwise, the code is exactly the same, and this clocks in at around 7 hours. Let's go even faster. Note that if a to the 5th plus b to the 5th plus c to the 5th plus d to the 5th is less than e to the 5th when looping through the e values, then there is no point in searching further for e, since e will only increase and can never make the equation true. This makes the code much faster since the speedup happens in the innermost loop, clocking in at around 1.5 hours. But we still have a long way to go. In the previous versions, note that I calculated a to the 5th, say, many times, since it was recalculated inside the innermost loop. However, it never changes except when the a loop changes. Here I hoist the a work to the outermost loop, and similarly for b, c, and d. Additionally, I only calculate the left-hand sum once to save on time. This brings the runtime down to 19 minutes of substantial improvement. Note that for all of these, you may wonder why I'm even searching for e. Isn't it already determined by a, b, c, and d? Mainly, if I calculate a to the 5th plus b to the 5th plus c to the 5th plus d to the 5th, and if the result is a 5th power of some number, aren't we already done? I could do that, but it turns out that this is much slower since calculating roots generally is slower than integer arithmetic. However, consider where this code lives. It keeps increasing n by 1, so why not have e be the same as n? That's what I do in version 7. The elimination of the innermost loop dramatically improves the speed from 19 minutes to 2 minutes. However, this is not the end of the story, as this is the fastest version I can make only using Python. In this version, I write the same program, just a snippet here, in C++. And this, with all optimizations on, destroys even version 7 clocking in at, wait for it, 1/4 of a second. All the way down from over 45 hours to just 1/4 of a second, a speed up of almost 650,000 times. Why the improvement over even version 7? The main reason is because everything in Python is a pointer, and that destroys caches on modern processors. In other words, if you need a program to go fast, don't do many Python operations. Hopefully that was interesting.